Hello and welcome to this research presentation and what started as a simple walk that eventually led to an astounding journey into new theoretical dimensions. And I'll bet you didn't think there was any mystery to feature scaling. Feature scaling is quite simple. Some of the less intelligent models think that if a number is larger, then it is more important. But what if age, measured in tens of years, is more important than income, measured in tens of thousands? So we need to scale these variables so that differences between values are neutralized, and those cognitively challenged models can then properly interpret variable importance. This is a correct statement. I can say that after research. But the question remains, why? Why is there no definitive answer to this question? Why isn't there a set of rules that we can follow that will lead to the correct choice of feature scaling in most, if not all, situations? Well, I thought that this project would take a couple of months because there are rules out there and I would check the rules and they would be confirmed and then we could move on. 12,000 experiments and a year and a half later, what we discovered left us gobsmacked. We discovered an entirely new dimension to the central theory of all predictive analytics. Oh, and I invented a new ensemble feature scaling algorithm with some exciting results. Now, here are some of the feature scaling selection rules that are circulating among practitioners. And we can see that in this case, they're really focusing on distribution, Gaussian distributions for standardization and non-Gaussian distributions for normalization. And here are some more rules, but instead of focusing on the distribution of the data, these rules are focused on the type of model that you're interfacing with. And here are even more rules, and these once again are focusing on the distribution of the data. And even Mr. Burkhoff, who said there was no definitive answer, attempted to put together some rules, some basic instructions for how to choose which feature scaler and when. Now, if we decompose the rules that you've just seen by schema, there are rules that are dependent on the data, and there are rules that are dependent on the model. And then I asked myself, but what happens if data-centric rule and a model-centric rule clashes? Well, it turns out there is a theory that handles all of these conflicts. Now, for the purposes of our experiments, we're going to choose a distance model because distance models require feature scaling. In our case, we're choosing the support vector classifier from the scikit-learn library, and we have specifically selected the RBF, or radial basis function kernel, which allows an internal calculation called squared Euclidean distance to be used to calculate distances. Now, this is the same calculation used by the k nearest neighbors distance model. So in effect, this one model is acting as a proxy for all distance models. And we're going to apply that support vector classifier model to no less than 60 data sets and 13 different feature scaling algorithms. We're covering the gamut with this one. Now, of the rules that were supplied, there were data-centric tests concerning outliers and distribution. So building an outlier detection model using the isolation forest algorithm, one of the most state-of-the-art available today, and computing the mean average anomaly score, we found nothing. We found no relationship whatsoever between any level or amount of outliers and any specific feature scaling algorithm. So, if the rule has to do with outliers, you can write it on a small piece of rice paper, take it into the garden, and burn it in your urn. We even tried custom scaling. Taking numeric predictors and scaling them with standardization and taking categorical predictors and scaling them with normalization, and it didn't result in any advantage whatsoever. There was no joy to be found down this approach. But now we're looking at distribution. So we started by building a random forest model that extracted the top 50% of the predictors contributing to model gain. And then we took and looked at the histogram of those distributions and then checked those distributions to see if there was any relationship between a data-centric distribution and a choice of feature scaling. No, in fact, it was even more confusing. As you can see in this one case, both standardization and normalization performed exactly the same with the same accuracy with data sets that have such wildly different distribution parameters? I think distribution is not looking too well at this point. Oh yes, and then we checked data distribution against an additional 89 distributions. Well, you get the picture. And there was one data set that was acting as an outlier all by itself, the Congress voting data set, to determine if you were a Democrat or Republican by how you voted in Congress. And you can see that all of the standardization, robust, normalization, all had the same best case accuracy, just for those 6 that are listed there, and all the rest, 7 more, were 7% behind in accuracy, and it makes no sense. So at this point, distributions are written off. And then we consulted model-centric literature. Now, in the case of these 5 research works, only 2 included a train test split. So only 2 of them are looking at predictive analytics. The others, there's no split, so there's no bias and variance. There's no prediction going on here. But still, it's just they're checking to see which algorithm worked the best, and that was it. So we did the same. We took all 13 algorithms, we ran them against all 60 data sets, and we can see that with the support vector classifier using standardization, this is in the top panel, the very top row, standardization achieved within 3% of the best accuracy on 77% of all the data sets. And going down to the blue panel, we can see that standardization performed at the top rank for half of all data sets. There's just one tiny, teeny, weeny little problem, and that is that standardization is not a fit for distance models. In fact, it is a direct misfit. And this is where all those other research papers ended. They would say that, well, this z-score standardization worked better with support vector classifiers and the radial basis kernel. We're done here. But why? Why did it work better? And why did normalization fare so poorly when in fact it was supposed to be the best according to the rules that were provided? So over a year in, and nothing was working. I began to think I was in apocalypse now with no end in sight, but then I found my Colonel Kurtz, and he was 75 clicks above the Dolong Bridge. What if the choice isn't between data and model centricity? What if these misfits, in fact, are part of an overarching theory that explains everything perfectly? I took a walk in the woods after interminable frustration, and then it hit me, and I knew what was happening. The theory of bias and variance explains everything. There are no conflicts when feature scaling is viewed through this lens. Note that the authors of this landmark work explicitly express data and the model as a single term. Mathematically, they are inseparable. And there is our wave-particle duality. Now, the model-centric view sees bias alone, just like all those research works that do not include a data partition. Now, in this case, if you want to fit between the feature scaler and the model to promote lower bias, but this is not predictive analytics. And considering that feature scaling distorts the original values, it doesn't work for interpretable analytics as well. This is just about wrong from every perspective, except perhaps unsupervised models. And after 30 years, it's time to set the record straight. Under the theory of bias and variance, a misfit between the feature scaler and the model will cause higher bias on the training data and lower variance on the test data, our very desirable condition. This is the correct view of feature scaling under the main theory of predictive analytics, and it is supported by both model-centric views for both generalization and predictive performance, with standardization surpassing all others with this distance model. But how do we check for concrete evidence of bias and variance? I mean, right now, it's circumstantial. Well, it hit me. By sequentially building models, by adjusting only the normalization range from 1 to 9, that should show lower bias and overfitting on the training data. So it's 1 to 9 on the x-axis, the training data is plotted in blue, the test results are plotted in orange, and the difference between the two is variance. Confirmation of the theory of bias and variance will occur when the blue line increases, as will the gap to the orange line. Lower bias equals higher variance. And note that there's always an inherent bias in each data set with respect to the model. So the results should not look clean like a picture in a book. But let's have a look anyway. Well, that does look like a picture in a book. That is exactly what we'd be looking for. And then there is this one. And then there's this one. And I know you're thinking, well, he's cherry-picked the best. Well, then there are these, and then there are these, and then there are these, and we could go on. The question is, Sherlock, do you see the pattern yet? What these results tell us is something quite extraordinary. So back to our two views of feature scaling. Well, the main definition there, transforming raw data to neutralize volumetric differences, big deal. We know what that is. But here is a new view of feature scaling. It imposes model-dependent controlled bias on raw data without losing the underlying information. Whoa. This is an area that has never been explored. What other transformations could be applied to raw data that could control bias without altering the underlying information, without losing the underlying information? But I wanted to visualize more about bias and variance. I wanted to see what is the reason why no definitive rules can exist, because that's the one part that's left missing. Now, Caltech says it can't be done. You say we can't do it, it's just a conceptual tool. So I did it anyway. Here is a research work that I published a little while ago, where I did some exploration into bias and variance to understand the nature of their relationship. Now, what you see here are 200 support vector classifier models of the IBM employee attrition dataset using standard scalar. And what you're seeing here is the variance. This is the difference between the bias and the training data and the test data results. That's the variance, and what you're seeing is the difference between those two plotted as this graph. And what you can see is variance makes it unpredictable. It is noise. And it doesn't matter if you change the learning model, it doesn't matter if you change the feature scalar, it doesn't matter what you do, it looks like noise in every single case. And that's why this is unpredictable, because variance is related to the chaos in the universe. And there's our first conjecture. This is why no hard and fast rules can be developed. It is because of the random inherent bias in the data sets themselves, combining with the variance created by the model. But we do have a rule now, and it's a rule that's a good place to start. Choose a misfit between the feature scalar and the learning model. Well, we've now established that bias and variance is in charge of feature scaling. So the time of discovery has ended. Now it's time for invention. And what we're going to be doing is building feature scaling ensembles. Now in this case, in the upper pipeline, we can see standard scalar going into a support vector classifier, and then robust scalar going into a support vector classifier. Now, robust scalar is normalization. It's just the range of normalization is trapped to the 25th and 75th percentile of each predictor. So it's normalization combined with standardization. And we're putting them into a stacking classifier in the top pipeline, that's logistic regression, who's looking at each input as a predictor. And then the voting classifier, which takes the probabilities of each input, adds them together, divides by 2, and then makes a choice from that. So it's strictly majority vote, basically. And we can see here in this plot that standardization, that's in the center, actually beats the stacking classifier. It beats an ensemble, and the voting classifier is only slightly better. So this is not the kind of performance that we would expect to see from ensembles. Now, expanding this picture a little fuller, the red bar shows the percent of data sets where a new accuracy record was set. So with the stacking classifier, 28% of the data sets had new accuracy, and with the voting classifier, 23%. So still, it's kind of iffy results for an ensemble. We even thought we could create a triple pipeline. And what happened was the theory of bias and variance got back at us, because by adding a third pipeline to this, we actually decreased bias. We increased variance. We made things worse. This is the Goldilocks and the Three Bears. This is the porridge theory of machine learning. It cannot be too hot. It cannot be too cold. And there is our conjecture number 2. Lowering bias is going to limit our ability to create the perfect feature scaling ensemble. Now we're going to try something different though. You know, on the left panel, we see a support vector classifier with the increasing accuracy in training. That's the lowering of bias in training and the widening of variance. But on the right-hand side is logistic regression with a ridge regularizer. And you can see that that regularization really does work. It's flattened out the overfitting on the training curve. It's flattened out the test curve. It's perfectly flat. So what's happening is regularization is smoothing out the bias slopes. And those bias slopes are what's causing controlled bias in the model as a result of transforms in the data. But what happens if we take logistic regression and make it into a feature scaling ensemble? Well, before we do that, let's take a look at just logistic regression by itself. And we can see it's performing, rather poorly. Standardization tracks within 3% of best performance on roughly 62% of the data sets, but that's only in the generalization performance. In predictive performance, it's way down the list. So what's happening is that the effect of regularization is altering what we would be seeing because of the theory of bias and variance. It's creating an unnatural obstruction in bias and variance, which is disrupting our results here. That is expected. But let's see how regularization plays all the way through with a logistic regression ensemble. Now, in this case, you can see that in the upper pipeline, we've got a standard scalar and robust scalar going to logistic regression inputs, all with L2 regularization and a stacking classifier. And in the lower pipeline is standard scalar with a wide range normalization going from 0 to 9. Also feeding logistic regression models and feeding a stacking classifier as well. So we have the stack rob output, which is robust scalar, and the stack 9 output, which is norm 9. The stacking classifier that combines standardization and robust scaling achieved generalization performance on 83% of the data sets, and a predictive performance on 73% of those same data sets. Now remember, we're not comparing model families, only feature scaling methods. But wow, I don't understand why this happened. Going even further, we can see that the stacked rob ensemble also generated new accuracy records on 43% of the data sets. This is striking. These results are quite stunning, and I don't understand why. It's logistic regression. So here's an area that needs to be explored a bit further. Yes, we have the data, and you'll see that in the case of these 60 data sets, you don't see anything about them. Even though they're all open source, they were open source at the time that this was used in this research, you never saw a detail about them. Not the name of a single predictor, not the name of a target variable, not any values, nothing. All you see is the metadata results of the experiments. Well, the practical guide to support vector classification needs to get an update with regard to section 2.2 on scaling. As you can see in the last line, we recommend linearly scaling each attribute to a range of -1 to +1 or 0 to 1. That is normalization, and that is not what you want to do. So, wrapping it up. Yeah, they're confusing and inaccurate, but now we understand why. Bias and variance are at play here. Chaos is at play here. And we know that support vector classifiers, well, need to be revisited. If you've built a model since 2003 and you're using normalization, go back and try it again with standardization. See what happens. We know about bias and variance and feature scaling now, and this is an area of tremendous research. It has not been touched. And feature scaling ensembles also in their infancy. Some ideas for future research include scaling standardization on the same sliding range like normalization to see if we can see a bias control plot in the training data. How about additional raw data transforms for controlling bias and variance? regularized regression models using lasso instead of ridge, using L1 instead of L2. And then, of course, there's still so much work to be done in feature scaling ensembles. I want to thank you all for your time and attention today. And I do hope that some of you are intrigued and proceed to take this into yet new and still unexplored directions. Thank you so much.